Today's lesson is on piecewise defined functions. Piecewise functions are exactly what they sound like. They are pieces of functions. For the first example set, we're graphing piecewise functions, and this here is what we're graphing. This looks completely different than anything we've ever graphed before. So we need to break this apart into 3 separate sections. And just a quick note before I do that, there's one function notation for each part of this graph, but we could rewrite this if we wanted to as 3 separate functions. We could write this as the first function being f of x is equal to negative x plus 1 on the interval of negative 1 is less than or equal to x less than 1. The second function being the line at f of x is equal to 2, limited to only one point at x equals 1. And the third function being f of x is equal to x squared, limited to all values greater than 1. So you could either write it like this with one function notation, or you could write it as 3 separate functions. Either way, you're going to achieve the same answer. You're working towards the same graph. So generally we see it in this top form, and that's what I'm going to work off of now. Let's graph the first function, negative x plus 1, restricted to the interval of negative 1 to 1 in yellow, or I'll highlight the section of the graph in yellow. The first step that we have to do is graph the function. So we need to graph negative x plus 1. That's in slope-intercept form with a y-intercept at 1 and a negative slope of 1 over 1. For right now, I'm going to graph this whole line, but we are going to erase some of it. We need to take a look at the restrictions. It tells us that this graph is going to occur between negative 1 and positive 1. Those are x values, of course, so I'm going to shade on my graph x values between negative 1 and positive 1. That means I only want the portion of the line that falls between those points, telling me I only want this portion of the line right here. Only what's in the yellow shaded section between negative 1 and positive 1. So I can erase my line, and I can limit my line to just the yellow shaded region. If I'm limiting my line to just the yellow shaded region, I also need to pay attention to my signs. At negative 1, we can include the point. At positive 1, we cannot. So that means I'm going to imagine that my line was still graphed. I know I erased it, but I had a point right here. This is going to be a solid point. And at positive 1, we're going to leave it as an open point. So after we erase that whole line, the portion of the line that's left is just this blue graph, or the blue line you see here in the yellow shaded region. Next, let's take a look at the graph f of x is equal to 2. That would be a line in the coordinate plane at y equals 2. But once again, we're going to want to restrict this to just one value. In this case, we're restricting it to one value because it says that x is equal to 1. So it's not telling us to restrict it on a certain interval. It's telling us to restrict it to a single value of x equals 1. It's also saying that x equals 1, so that would be a solid point in the coordinate plane. We can get rid of the rest of the line. We're just keeping that single point. And the last graph is x squared, restricted to values greater than 1. So x squared, we know our key points are at negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Okay, we only want the portion of the graph that falls on the interval greater than 1. meaning we only want the portion of the graph that falls in this green shaded area. So I can erase the rest of the graph and leave just from +1 on. Also note that at +1, it's going to be an open circle. The point is not included. I can erase the rest of the line. All right, so my final graph is just what's left here. So it's just portions of our original equations. Now that we're done graphing, I'm going to erase my shaded areas so we can see the final answer. All right, here is our final graph. We have different parts to the function. Make sure that your graph always passes the vertical line test, meaning that if we drew a vertical line down the graph at any point, it's only going to intersect the graph at one location. And check this out right here. This is an open circle, not included. Open circle, not included. Closed circle is included, and that does pass the vertical line test because there is only one point on that line. All right, besides from graphing this, we also need to indicate the domain, meaning we're going to have to look at the different portions of the graph and identify what the domain is. So remember that if you have an open circle and a closed circle on the same point, the closed circle will always override that open circle and you include the value. But in either case, the domain is going to start right here and it's going to go towards +infinity forever. Yes, we are omitting a value right here, but at that value of x = 1, we also have a closed circle. This point will trump the open circle, so therefore we are including it. And then we can see that this graph goes on forever. So we know that the domain is going to be from -1, including -1, to +infinity. The domain is going to be at 0. No, sorry, the range is going to be at 0, and it's going to head up forever. Yes, we have a couple open circles. We need to clarify what we're doing with those. At 0, we don't have any other points. So on this line here, the only point we have is this point, and it is not included. So we will not be including 0. But at this point right here, we have an open circle that I just drew an arrow to, but on this point we have a closed circle because remember a solid line is made up of solid dots. So this solid point is going to override that open circle and we are going to include it. And then this graph goes on forever. So yes, we can include all points from 0, I guess I should say, not including 0, and then everything from there to +infinity. Let's take a look at the next graph. So we have 3 functions. We're going to graph the pieces to each one of these functions, starting with my first graph of 2x + 5 restricted to the interval of -3 and 0. 2x + 5 is in standard form. I'm going to go up to 5 and plot a point. My slope is +2/1. That means I'm going up 2/1, or we can go down 2/1. All right, we are going to have to restrict this between the interval of -3 and 0. -3 starts here, and we're going to 0. So we want all parts of the line that fall in this yellow shaded region, meaning we want from -3, including -3, so including this point, to 0, not including that point. We're going to erase the rest of our line, and we're going to only include what falls in that yellow shaded region. Next, we're going to do the line at f of x is equal to -3, restricted to the point at 0. So -3 would be the line here. All right, and then we are looking at just one single point when x is equal to 0, and it does say it's equal to it, so that is going to be a solid point on that line. We don't want any other parts of the line, we only want the indicated value of 0, so I can erase the rest of that. And last we have -5x restricted to all values greater than 0. So -5x is also in slope-intercept form. We don't see a y-intercept because that is because it's just 0, meaning we plot a point at 0. It's a negative slope, so go down 5 over 1 or up 5 over 1 and graph your line. This is restricted to all values greater than 0, so all values of that line that's in this green shaded region. Also note that you are not including 0, so it's going to be an open circle on this line at 0. And this here is my final answer. If I erase the shaded regions, you can see what the final graph looks like. Make sure you can clearly see your open or closed points. And then let's evaluate or write the domain and range. So for the domain, it appears as if the function starts here and then it goes on forever. You can see down there it does continue forever in the positive direction. So the domain starts at -3, including -3, and it goes to positive infinity. Yes, we have a few open circles, but on the x value of those open circles, we also have a closed circle, so that will override it. The range appears to start here, not including that value, goes down forever. Again, we have some parts where the graph looks like it might start or stop, but then somewhere else on the graph, there's another point. So always look at the graph as a whole when you are writing the domain and range. For this, the domain starts at -infinity because our most negative value always comes first, and it goes to +5 with a round bracket because this point is not included. Okay, analyzing a piecewise defined function, meaning we are evaluating these functions. If you're evaluating the function, you want to evaluate the function using the appropriate restriction. So you have to pay attention to these restrictions when you are evaluating. For the first function, we have 3 separate functions. We have x squared restricted to values less than 0. We have a value of 2 restricted to the value at 0, and 2x plus 1 restricted to values greater than 0. So when we are evaluating a function, we need to make sure that whatever our inside value is, you need to match it with the appropriate restriction value, meaning -2, is it greater than 0? I would say no. Is -2 equal to 0? Also no. Is -2 less than 0? Yes, -2 is less than 0. So we are going to use this first function while evaluating -2. That's the only function you use. So for part A, we're going to evaluate f of -2 using the function of -2 squared. And match my colors, so I'm using everything with this green highlighter for part A. When I simplify this, -2 squared is equal to 4. So f of -2 is equal to 4. That's your answer. That's your only answer. You do not substitute that value into any of the other functions. Okay, for part B, we have a value of 0. So we need to think to ourselves, is 0 greater than 0? No. Is 0 equal to 0? Yes. So for part B, we're going to be using the function f of x is equal to 2. And this one you don't really need to do any work because that's going to be your answer. But it's saying that when you evaluate at f of 0, it's equal to 2. You don't have anything to substitute in. That is just your answer. And for part C, we have a value of 2. Oops. So once again, where does it apply to? 2 is greater than 0, so we're going to be using this function here. F of 2 is equal to 2 times 2 plus 1. This is equal to 4 plus 1, or f of 2 is equal to 5. All right, those are your 3 answers. Those are your only 3 answers. Do not substitute those values anywhere that they do not belong. They have specific restrictions. Make sure you use them. Number 2. Number 2, we have 3 functions, -x plus 1, restricted to -1 and 1, 2, restricted to a value of 1, and x squared, restricted to values greater than 1. Part A, we're looking for f of -2. Does -2 fit into any of these restrictions? It is not greater than 1. It is not equal to 1. It is not between -1 and 1. So therefore, f of -2 does not exist on this graph. That is your answer. If we were to graph this function, there would be no value at -2. Therefore, it does not exist. All right, b is a value of 0. Is 0 greater than 1? No. Is 0 equal to 1? No. And lastly, is 0 between -1 and 1? And yes, it is. So for part B, f of 0, you're going to use the first function, meaning we're going to have -0 plus 1. That simplifies to -0 plus 1, or just 1. So f of 0 is equal to 1. And for part C, we're evaluating the function at 2. So 2 would apply to the value of x is greater than 1, meaning we're going to use the function x squared. F of 2 substituted into x squared would be 2 squared. That's equal to 4. So f of 2 equals 4.